Hi folks, welcome back to 5.3, and this is a video number 2. So here we're going to talk about the fundamental theorem of calculus, and it comes in 2 different parts. And in this section, we're going to focus on part 1. So here we have a definition of the fundamental theorem of calculus, part 1. If little f is continuous on the interval a to b, then the function capital F of x equals the integral from little a to x of f of t dt has a derivative at every point x in the interval a to b, and df dx equals ddx, the integral from a to x of f of t dt, which equals f of x. Now, I know that's a mouthful for sure, and it's pretty hard to make sense of what it is we're really trying to find, but in other words, this is what we're saying. The derivative of the antiderivative, okay, that gives us the original function. So if I take the derivative and then I take the antiderivative, those undo each other. Or, as this definition is saying, if I take the antiderivative and then I take the derivative, I get back to the original. So let's see how this is applied. I know that conceptually that part makes sense for us, but we're going to look at a few specific applications of this definition. So let's take a look at example number 3. For example number 3, we have a case where we can say that the bottom bound is a constant, so negative pi over 2, and the top bound, b, is just x. And let's take a look at this definition, okay? So here we have the derivative of the antiderivative. Well, that should give me my original function. Okay, that's what we're going to be seeing. So at the end, I shouldn't have a sign, like sine and cosine. I shouldn't have a sine, but I should still have a cosine. But let's take this one piece by piece. We're going to keep the d dx on the outside, and we're going to take a look at what the integral from negative pi over 2 to x of cosine t dt is. So let's start with the antiderivative of cosine. The antiderivative of cosine is sine t. And then instead of a plus c, I'm going to draw a line. I'm going to put my b value at the top and my a value at the bottom. And I'm going to simplify that. So d dx of, you're going to plug in the top bound, so sine x, minus, plug in the bottom bound, sine of negative pi over 2. Okay. So now we're going to take the derivative of sine x, and then we're going to take the derivative of sine of negative pi over 2. The derivative of sine x is cosine x minus, this is a constant. And what's the derivative of a constant? 0. And so we end up just with cosine x as the derivative of the antiderivative, or our original function. Okay, so our original function was cosine x. Okay, let's take a look at part B. So this time, we've got a equals x, so our lower bound is the variable, and b equals the constant is the upper bound. And I see the d dx and I see the antiderivative, so I know I'm looking for the original function. So let's take this step by step like we did in part A. d dx of The antiderivative of cosine t is sine t. Draw the bar, negative pi over 2x d dx of, plug in your bounds, sine of negative pi over 2 minus sine of x. So very similar to what we saw in part A, with a very subtle change. This constant is now in the front. So when I find my derivative, I'm going to have 0. Well, let's stay constant with our colors. We're going to have 0, and then it's going to be minus the derivative of sine, which is cosine x. Or we could say that our original function this time was negative cosine x. Okay? Let's take a look at part C. So in part C, we have something a little bit different. We have that a is a function of x. Our lower bound is some function that involves x. And our upper bound is some other function of x, but they're both functions of x. So we're going to start the same way and see what happens, but because I have the derivative of the antiderivative, I know my answer will be the original function. Okay, so d dx, I know from all the other examples I've done so far, the antiderivative of cosine t is sine t. Draw a bar, x squared on the top, 2x on the bottom. Okay, d dx of sine of, plug in the top bound, so sine of x squared. So the x is squared, not the sine x. Okay, minus sine of 2x. Okay, well, I take a look at this and I notice that in this case, I have no constants. So I didn't have any constants like I did in part B or part A. And so that means I'm taking derivatives of functions. So this we could write as take the derivative of sine x squared minus the derivative of sine 2x. Okay. So the derivative of sine x squared is cosine x squared, but here comes that chain rule, times the derivative of x squared, which is 2x. So this was my inner function, and then I had to multiply by the derivative of it. So we can say because it's a function of x that we're going to need chain rule. Minus, let's see, the derivative of the second part. Derivative of sine is cosine of 2x times 2 for the same reason that I have 2x is some function of x. So I need to multiply by the derivative because I'm taking derivatives. And so in the second one, I'm using chain rule as well. And if we clean this up, we'll get 2x cosine of x squared minus 2 cosine of 2x. And this is our original function. Okay. So we have a few cases here where one of the bounds is a constant, where we switch the bounds in part B, and then in part C where they're functions of x. So we're going to take a look at this one more time with a different function just to practice this a little bit more. So here's example 4. Okay, so we have a case this time where we've got our A is a constant. In this case, it's 1. Our b is x, or our top bound is x. And I have d dx of an antiderivative, so that's going to give me the original function. Now, the key thing here is you have to have that d dx in the front. If you don't, then it's just asking you to find the integral. But what we're asking here is to take the derivative of the antiderivative. Okay, so we're practicing that formal definition, that fundamental theorem of calculus. Okay, so d dx of, this one's a little trickier, but 1 over 1 plus t squared, well, that is really arctan of t. All right, so it's one of those inverse trig functions that comes up pretty frequently in Calc 2. All right, so that's why I wanted to use this one as an example. Draw a bar, put the x, put the 1. Now we're going to find the derivative, but first we have to plug in our bounds. So arctan of x minus arctan of 1. Well, just like last time, looks like I've got a constant here. So at the end, my original function is just going to be the derivative of arctan, or 1 over 1 plus x squared. So this is my original function. Okay. Sorry, it keeps freezing on me. Still frozen. Okay, so let's take a look at part B. We've switched our constant to be at the top, 1, and we've switched our x to be at the bottom. So if we think about how this is going to change, well, this part is still the same. Arctan of t is my antiderivative, but this time I'm plugging in 1 and then subtracting when I plug in x. So that will give me d dx of arctan of 1 minus arctan of x. And the constant is in the front, so my answer will actually be negative 1 over 1 plus x squared because I'm subtracting. All right, and so that's my original function for part B. Okay, part C here. We've got that different case where we have a function on the bottom and we have a different function at the top. Okay. So I know I have my d dx of arctan of t, but I'm going to plug in x to the 4th, and then I'm going to subtract when I plug in 3x. So this will give me the derivative of arctan of x to the 4th. Oops. Writing too fast here, arctan of t. So arctan of x to the 4th minus arctan of 3x. Now, just like my other example, what I've got here is the case of chain rule. I have to use my chain rule. So when I take the derivative of arctan of x to the 4th, I get 1 over 1 plus x to the 4th squared times the derivative of x to the 4th, which is 4x cubed, minus 1 over 1 plus 3x squared times the derivative of 3x, which is 3. And if we clean that up, we'll get 4x cubed over 1 plus x to the 4 times 2 is 8, minus 3 over 1 plus 9x squared. And that was our original function before we took the antiderivative and then the derivative. Okay, let's stop here, come back for part 3.